Bus or car hardly moves at constant velocity. Obviously, uniform motion model is very restrictive. A more realistic model is the one who is able to account for the change in velocity or acceleration, the accelerated motion model. For simplicity, unless specified otherwise, we will assume throughout this course that the acceleration is constant. That is to say, yes, the bus changes its velocity over time, but these changes happen at constant rate. If we are able to deal with the change from constant velocity to changing velocity, we should be able to extend the concept to the change from constant acceleration to changing acceleration. So let's get back to our journey on NUS internal shuttle bus. Imagine for a moment these two events. The bus is moving at 6 km per hour, passing Ridgeview residents with the direction given as such. So these two information, the speed of the bus and the direction, tells the velocity of the bus. And 2 minutes later, the bus is found climbing up Kentridge Hill at 5 km per hour with the direction given as such. Obviously, there is a change in velocity, which implies that the bus undergoes acceleration. The question is, how to compute this acceleration? Acceleration is given by the change in velocity over time taken for that change to take place. Because velocity is a vector quantity, whereas time is a scalar quantity, naturally, acceleration is also a vector quantity. The change in velocity refers to the difference in the velocity of the bus when climbing the Kentridge Hill to velocity of the bus when passing by Ridgeview residents. The problem is that we cannot, I repeat, we cannot simply subtract 6 km per hour to 5 km per hour and divide by 2 minutes. The 5 km per hour and 6 km per hour are the instantaneous speed of the bus, not the velocity. We need to somehow take into account the direction of the moving bus. This is where things get a bit complicated, just a little bit. So follow my explanation for the next couple of minutes carefully. Let's start with the final velocity first. In case you have not noticed, there is an angle that accompanies the arrows. These are the angles that the arrows make with the horizontal line. 45 degrees for initial velocity and 60 degrees for the final velocity. By the way, I invented these numbers, so don't think too much why they are 45 and 60 and not other numbers. The point here is, given the length of the arrow, which indicates the speed or the magnitude of the velocity, and the angle it makes to the horizontal, we can mathematically write down the velocity vector of the bus in terms of I hat and j hat. This is where trigonometry comes in. Remember the section on resolving the hypotenuse of a right triangle using sine and cosine? The horizontal component of the velocity is given by the projection of the arrow to the horizontal x-axis. There is no actual x or y axis drawn here, but use your imagination. It is important to develop such visualization skills in physics. Anyway, the horizontal component of the velocity is given by cosine 60 degree of the hypotenuse, which is 5 km per hour cosine 60, and the vertical or y component of the velocity is given by sine of the hypotenuse, which is 5 km per hour sine 60. Moving on, the horizontal and vertical component of the initial velocity can be computed in similar way. We pause here because I want you guys to meditate a while and convince yourself that the components are computed accurately. If you are convinced, the next step is to work out the computation. I will not spell letter by letter what is written here. Instead, I will highlight things which you need to take note. First, the numerator is a difference in velocity, the final velocity and the initial velocity, in I hat and j hat form. The denominator is of course the time span, which is 2 minutes. Second, notice the sign. When resolving the velocity vector using sine and cosine just now, I didn't tell you about the sign. By convention, any vector pointing to the left or pointing down is negative, whereas any vector pointing to the right or pointing up is positive. In that sense, we follow the same configuration as plus-minus sign in Cartesian coordinate. So do check if the signs I put are consistent. Third, pay attention to the units. The numerator is in km per hour. The denominator is in minutes. They are not consistent and they are not SI units. So you have to convert the units to SI units, and in so doing, you will have to change the numerical value as well. 1 kilometer is 1000 meter, 1 hour is 3600 seconds, and in case you forget, 1 minute is 60 seconds. the unit of velocity is meter per second, whereas the unit for time is second. So change of velocity over time will give you a quantity having a unit of meter per second, or meter per second square. Fourth, how do you know whether the answer is making sense? Well, we can graphically check the answer. If we draw the initial velocity and the final velocity factor together, the acceleration factor is presented by the green arrow. If you are not so convinced, think about it. The acceleration factor is the difference between the final velocity factor and the initial velocity factor. That means, if we add the acceleration factor to the initial velocity factor, remember how to add factors graphically? The head of one factor follows the tail of another factor. That should give us the final velocity factor as expected. This acceleration factor in terms of unit vector I hat and j hat is given by the result we computed earlier. 4.08 meter per second square along horizontal and minus 19.83 meter per second square along vertical. The negative sign indicates that it is pointing down. By the way, by right, the length of the vertical component should be about 5 times of the horizontal component, in accordance to the ratio 19.83 to 4.08. I did not draw the factors arrows exactly up to scale, resulting in this rather bad example. Lastly, in the same way average and instantaneous velocity were defined in the last video, notice the way I define acceleration here. Do you think I was computing average acceleration or instantaneous acceleration? I was computing average acceleration. As you would have probably imagined, hardly the bus will be able to move at constant acceleration from RVR to KR Hill. It has to decelerate to stop for traffic at YIA's roundabout and accelerate again to continue climbing up the hill after passing the roundabout. Just like velocity, the bus's acceleration is not going to be constant. We can thus define the so-called instantaneous acceleration at any particular point in time in similar manner to average acceleration, but with the difference in time made so close to zero. In short, acceleration is the first derivative of velocity. Next point. Can we compute the distance that the bus travels as it accelerates? Yes, we can. To simplify matters, let's constrain the discussion to acceleration along a straight line. Consider this scenario. At one point in time, the shuttle bus is found to be moving at 1 meter per second. Assuming that it is accelerating at 2 meter per second square for 5 seconds in the same direction as it moves, what is the final velocity of the bus and how far has the bus traveled after 5 seconds? The answer to the former question is straightforward because we have learned that acceleration is the change in velocity over time. So it's just a play with algebra and you can compute the final velocity after 5 seconds given by 11 meter per second. We'll pause here to make sure you get it. The answer to the latter questions requires more analysis. Now you learned from the previous lecture that displacement is given by velocity multiplied by time required to complete that displacement. It is thus clear that the time in this context is 5 seconds. How about the velocity? Are we to use the initial velocity 1 meter per second or the final velocity 11 meter per second? It is neither. If you think about it, the bus moves at 1 meter per second only at the exact beginning. If we are to use initial velocity in the equation, our answer will be too short. On the other hand, the bus only moves at 11 meter per second only at the exact end. If we are to use final velocity in the equation, our answer will be too long. As a matter of fact, as the bus completes its course, it will move at velocity somewhere in between 1 and 11 meter per second. In fact, because of the constant acceleration, the velocity continuously changes all the time. So what velocity should we use in the equation? Think carefully. Use your imagination. If the bus changes its velocity at constant rate, that is to say that the bus is moving at constant acceleration, the most appropriate value to be used will be the average of the initial and final velocity. Since the initial velocity is given and the final velocity was computed just now, we can then use these values. Alternatively, we can express our answer in terms of acceleration and time, which are also known from the problem. 1/2 a delta t squared plus vi times delta t. Do remember this equation unless you know how to derive them on the spot during exam. The rest is calculator punching. So far so good? Okay, so let's recap what we have discussed so far. What are the relevant quantities in accelerated motion model? Acceleration, which is assumed to be constant, final velocity, initial velocity, time span to reach intended final velocity from initial velocity, and how far the object has been displaced during this time span. In essence, the knowledge of any three of these five quantities can be used to deduce the rest. A couple of equations are readily available, such as the equation from the definition of acceleration itself. Then just now we derived the equation that computes displacement given the acceleration, initial velocity, and time span. Another useful equation is the one where we could eliminate time span. That is the equation which relates final velocity, initial velocity, acceleration, and displacement. I provide the derivation here, which I expect you guys to work out again for exercise. It is not difficult to derive conceptually because what I did was simply to substitute the first equation to the second equation to eliminate delta t. These equations are in red boxes. You know what it means. And once again, do not forget the underlying assumption in this model. The acceleration must be constant, which means you can only apply these equations under that assumption. One phenomenon where constant acceleration model is directly applicable is freefall motion. It is called as such to describe any fall which is purely due to gravitational attraction. How do we visualize or experience freefall motion? Well, just get yourself to some kind of high structure, a skyscraper, a bridge, a high cliff, walk to the edge and make that big leap of faith into the void. But of course, please do so with the safety of a bungee cords. Everything on the surface of Earth will fall at the acceleration of 9.81 meters per second square. Everything, you hear me, everything. You, me, tennis ball, basketball, feather, everything. Now this may sound like a ridiculous concept. Your experience will tell you that if you drop a sheet of paper and a basketball from the 10th floor, surely the basketball will reach the ground earlier. That is true. The only problem is that the constant acceleration model is not applicable to describe that phenomenon. Because of air resistance, the ball and the paper do not fall at constant acceleration. So those equations are presented in the previous slide are no longer valid, at least not completely. You need more complex model to describe the physics of falling paper. For instance, check this out. But in the absence of air resistance, the ball and the paper are falling at the same rate of 9.81 meters per second square. If they are released from the same height, they will follow exactly the same trajectory in time and reach the ground at the same time. Guaranteed. If you don't trust me, click on these links. For copyright reason, I am unable to insert the full videos directly here, so I encourage you to view the videos yourself. By the way, this magic number of 9.81 meters per second square is called gravitational acceleration and is denoted by small case g. If you ask me why the magic number, well, we will learn how to derive this number later on, so relax.